In this video we solve problem 8 of Unit 15. In this problem we have 3 wires, all infinitely long and parallel. It's wire A, B and C. Wires A and C have the current has the same direction, and in wire B the direction is opposite to the other two. The 3 wires are in the same plane. So the first wire has 30 amperes, the second one 10, and the third one 20. And the distances between A and B are 3 centimeters, and between B and C is 5 centimeters. So between A and C, this is 8 centimeters. So first of all, they ask us to find the force per unit length exerted on wire B. Okay, so before getting into that, we have to remember that if we have 2 wires, parallel and infinitely long, wire 1 and wire 2, the force per unit length that the first one exerted on the second one is equal to mu sub 0 divided by 2 pi times the current of the first one, the current of the second one, and divided by the distance between them. Okay, so we're going to have this, we're going to apply this, and the idea that if both currents are parallel, if they have the same direction, the force is attractive, and if they have opposite direction, the force is repulsive. So with these ideas, we can apply it very easily to our case. So we can begin by the force exerted on B provided by the wire A. So we can calculate the force per unit length, and this is going to be equal to mu sub 0 divided by 2 pi times the current in A, the current in B, divided by the distance between them. Okay, the distance between A and B. So the distance between A and B is 3 centimeters. The currents, we have them here. So this is EA, this is IB, this is IC. Okay. And mu sub 0, we also know that mu sub 0 is 4 pi times 10 to the minus 7 Tesla meter divided by ampere. So if we put everything together, we have that this force, its magnitude, is equal to 2.10 to the minus 3 Newton per meter. Okay, to discuss the direction, we just have to see that current A and current B have opposite directions, so this force is repulsive. So repulsive force applied on B coming from A has to have this direction. So this is FAB, or if you want, DFB DDL. Okay, so I've discussed with you that this has to be in the positive direction of the x-axis, because I'm placing the x-axis here. Okay, this is going to be, if you want, the y-axis. I'm putting the origin in wire A. So this is the first one. We apply the same for the second one. So this would be C on B. DDL has to be equal to mu sub 0 to pi, the intensity of C, current of C, current of B, and the distance between C and B. This distance between C and B is equal to 5 centimeters. So if you put everything together, this is a modulus, if you put everything together, CB DDL, this gives you, provides 8 times 10 to the minus 4 Newton per meter. And to know the direction, we just have to see that wires B and C have opposite directions, so the force is repulsive. So the force has this direction, the FCBDL has this direction, so this is minus I. So all in all, the total force exerted on C coming from, it's the part that comes from A plus the part that comes from B, so this is B, this is C on B, okay? And this, adding these two up, you see that this is a positive force of 1.2 times 10 to the minus 3 Newton per meter in the positive direction of the x-axis. Okay, so the force that A exerts on B is bigger than the one that C exerts on B. Okay, so the y would be moving towards the right. Okay, so towards the right. Okay, so now we have to go to B and we have to determine the distance from A and see where the wire should be placed so that it is in equilibrium, and then discuss if it is a stable or an unstable equilibrium. Okay, so I'm going to go to this following page, and then what we need now is that the total force on B, so this is section B, the total force on B should be 0. So this means that the force of A on B should equal the force of C on B, the modulus, because we know that the directions are opposite, okay? So this means that mu sub 0 divided by 2 pi times the current in A, current in B, the distance between A and B has to be equal to mu sub 0 divided by 2 pi, current on C, current on on B, divided by the distance between C and B. Okay, so this means we can take these away. Also the current in B, this means that we need to find a place where the current in A divided by the distance between A and B has to be equal to the current in C divided by the distance between C and B. Okay, so we're going to call, I bring back our drawing. Okay, so this is X, so this was the current in A. This is the current in B, sorry, and this is the current in C. We know that this distance is 8 centimeters. We're going to call this X, okay, so this means that IA divided by X has to be equal to IC divided by 8 centimeters minus X, okay. So from here, we can see that X times IC divided by IA has to be equal to the 8 centimeters minus X. So from here, we can see that X has to be equal to the 8 centimeters divided by IC divided by IA plus 1. So from here you can get that the distance has to be equal to 4.8 times 10 to the minus 2 meters. Okay, so it was 3 centimeters. You have to put it further away from the section A. Okay, in that case both forces per unit length are equal and cancel each other because they have opposite directions. Okay, so now we have to discuss if the equilibrium is stable or unstable. So to discuss this, imagine that x grows a bit, okay? If x grows a bit, this would mean that the force of A on B is going to decrease, while the force on C on D will increase because we get closer to C. And this would provide you a force that will go towards the left. If x decreases, then we have the opposite. This force will increase, the one provided by A, while the one provided by Z will decrease. So you would have a force to the left. So whenever you try to move, there's going to be a restoring force. So this means that the equilibrium is stable.